the test was scheduled for today. We are very, very far behind, but I'm not in any hurry. So what I've decided we're going to do is we're going to make exam 2 next Tuesday. It'll cover the packet on test 2 material. That's all that will be on the test. And then the exam 3, which is scheduled for, it was supposed to be, what is it, the 23rd? I'm thinking that we don't even do a test 3 and we just make that like the final. You know, so we don't try and squeeze a third test in, just make it the final. But that means we'll have to adjust how the tests are weighted. So I think we just need to, when we cross that bridge, when we get to it, we'll cross it. But I'm not going to make it where it's going to hurt you by us not having that third exam. All right. So if we need to make the, I have to look at the weights, but I'll weight them so that it's most advantageous to you. That makes sense. All right. But let's get another test under our belt, and then we'll kind of go from there. We've finished up, I don't know, it's so long ago. See if you remember this. I remembered as soon as I looked at it because we were having this major problem, remember? With everyone was, well, not everyone, but there were a lot of people that were freaking out about this whole thing. And so let's get back on track and continue talking about this whole number system that we have and not get bogged down on how crazy this may seem, but instead just how are we going to use it to help us do what we need to do. The major thing today to start off is to remember that prior to, let's say today, if someone tried to ask you to determine what the square root of -1 was, that it didn't make a whole lot of sense. We know that something like the square root of 4 equals 2, right? Why is that true? Because when you square 2, what do you get? 4, right? So in the past, if we say the square root of a number is something like here 2, the reason why it is because if I square that 2, I should get back the number underneath. That doesn't quite work easily when you have a -1 under here. Because if I'm saying that by definition, I, the imaginary unit, is defined to be the square root of -1, then what this means is that when I take I and I square it, I should get what? So if the square root of 4 is 2, that means that when I square 2, I should get the 4 underneath, right? So if the square root of -1 is defined to be I, that means when I square the I should get what's underneath here, right? I should get -1. And we've always been told that when you square something, it's always positive. But I is the one number that when you square it, you actually get negative. You get -1. And that's the definition of I. It is the only number that has that property. So let's just keep that in mind as we move on to today's stuff. There's the homework from last time. So we were solving quadratic equations last class. We were using factoring to do so. And we're going to continue solving quadratic equations today. But now we're going to have the ability to deal with the square roots of negative numbers. So when we look at this square root of -4, here's how I'd like for you to look at it. -4 is the same as 4 times -1. Do you agree? And then we have a property of square roots that says you can now split this into 2 separate square roots. So the square root of -4 is the same as the square root of 4 times -1, but that's the same as the square root of 4 times the square root of -1. What is the square root of 4? 2, and what is the square root of -1? By definition, I. Bless you. So the answer is 2i. Okay? How about square root of 9? That'd be 3i. We do the same thing, right? Because there's a negative. So the idea is that any time that we see a square root and a negative underneath it, we know that an I is going to pop out of it, right? And then it's just a matter of, can we figure out the square root of the number? So when I'm looking at this, I see the negative right there in blue. I know my answer has to have an I. Then I look at the 9, and I ask myself, do I know the square root of 9? Square root of 9 is 3, so I'm going to need a 3i. Okay? Now, if you don't have a negative underneath it, right, like this square root of 72, you don't have a negative, then you're never going to get an I to pop out. So the square root of 72 should not have an imaginary unit involved in it at all. But when we write the square root of 72, that is not what we consider to be completely simplified. And the reason is because you can rewrite 72 as what, 9 times 8? Do you agree? Is that the only way you could write it? There's a bunch of different ways you could write 72, right? Well, let's look at it this way. 9 times 8. Do you agree that that's square root of 9 times square root of 8? What's the square root of 9? 3. And now look at the 8. Does the 8 have a perfect square in it? In other words, a number that you know is a perfect square. 4 times 2, right? And then you could split that up. What's the square root of 4? 2. So how am I going to connect the 3 and the 2 together here? Multiplication, right? Times. And then square root of 2. Can't do anything with that. 3 times 2 is 6. Square root 2. Do y'all see how I did that? Now, that's one way to do it. I could have also, if maybe I would have seen this to begin with, I could have realized that 72 is 36 times 2, right? If I would have realized that to start off, then I could split it into 2 radicals like this. And what's the square root of 36? 6. And this would have been 6 times square root of 2. So you get the same answer either way. One of them took a little longer, but maybe 9 times 8 is easier for people to have thought of when it came to 72. Now, why don't I go any further with the square root of 2? You can't go any smaller, right? There is no perfect square in there other than 1 at 1, right? But there would make no sense to pull a 1 out here because it wouldn't change anything. All right. So we'll leave this. We don't need to fill that in. All right. So this complete the property. They just want you to realize again that you can split this into 2. All right. Just remember that if you have the square root and you have multiplication between these two, that you can turn it into this. What you want to be careful with is this. Careful. Don't do this. That is not true. All right. See, I split this square root, and it was 4 plus 9. I split it into square root of 4 plus square root of 9. That is not allowed, right? Because what is the square root of 4? 2 and square root of 9? 3. So you would be saying here that this is equal to 2 plus 3 is 5, right? Is the square root of 13 5? No. Square root of 25 is 5. So this property, doing it this way, does not work. It does work, however, if it's multiplication between the two. All right, so just careful on that. All right, so let's see if we can do these. So I'm looking at square root of 12. Can you think of a number, a perfect square, that goes into 12? 4? So rewrite 12 as what, 4 times 3? That's square root of 4 times square root of 3. So that's what? 2 square roots of 3. By the way, what are our perfect squares? I'll put them on the board just to make sure we're all together on this. The perfect squares. What? 1 squared is 1. 2 squared is 4. 3 squared 9. 16. 5 squared 25. 6 squared 36. 7 squared 49. 8 squared 9 squared. 10 squared. 11 squared. 12 squared. 13 squared. We're starting to get into dork territory, aren't we? Yes. 14 squared. You need to know at least the first 12 or 13. I mean, those should be ones that you kind of just from memory you've seen. All right. So what we were doing here when we were looking at the number 12 is we were saying, do any of these numbers go into 12? And we said, oh, 4 does. And that way we can break down the square root of 4 to be 2. How about 18? Do you see a perfect square that's in 18? 9, so 9 and 2. So we can break this down to be square root of 9 times 2, square root of 9 times square root of 2, which is 3 root 2. Now, would it be wrong for me to write it this way? Root 2 times 3. Do they mean the same thing? This means take 3 and multiply times the square root of 2. This means take 2 and multiply, or square root of 2 and multiply times 3. These are the exact same expressions. The reason why we like to put the number in front of the root is because some people might think, oh, I should put 2 times 3 and make that a 6, and they think this is square root of 6. But that's not true. The 3 is not underneath the square root. So to help you not make that mistake, we like to place the 3 out in front of the square root. Does that make sense as far as just order of things? But in terms of multiplication, you can always flip the order of multiplication. It doesn't change the answer. All right, how about 45? See a perfect square in there? 9 again. This time 9 and 5. So this is going to turn into, let's try and do it without that next step. Square root of 9 is 3, and then square root of 5 can't do anything, right? So 3 root 5. 72, we just did that one, didn't we? We don't need to do that again. 980, not so obvious. Any of those numbers go in there? So maybe you break your calculator out. You start trying to divide numbers into 980 and start using that list. Except that you never want to use 1 because that's not really going to change anything. Does 4 go into that? So get your calculator out if you have it. 4 and 245. So we know what we can break down with 4, right? Let me see if I can go any further. 980 divided by the next one on the list is 9. No. 980 divided by the next one on the list is 16. No. 49 and 20 works. That's an even bigger one. Wonder if anything bigger than that works. Well, I think 49 and 20 is probably a good place to start. 49 times 20. That turns into 7 root 20. But now you have to look at the 20. Can you break the 20 down? Yes, 4 and 5. So 7 and then root 4 times 5, which is 7. Now, what's the square root of 4? 2, so multiply 2, and then the square root of 5, we can't touch that. And then 7 times 2 is 14. Root 5. This is what we mean when we say simplify a radical. breaking it down as far as we can so that whatever's under here cannot be broken down any further. 75, 25 and 3, 5 root 3. Any questions? No? Let's do it. Let's call it the final. We'll just meet one more time on Tuesday, and that's it. I would if I could, okay? All right, so look, on these problems, we don't want to get all caught up with, oh no, there's a negative, what do we do? But we want to know the negative's there, right? Anytime we see a negative under a square root, the negative will go away and an I will appear, right? So I'm just going to put down here square root of 36. The negative is gone, but I'm going to put times I out here. Now the square root of 36 is just like what we just did. What's the square root of 36? 6. So this just becomes 6I. That's the answer. Next one, square root of 72. The negative is gone. I slap an I on the end. What was the square root of 72? We did that up here, didn't we? Square root of 7. 6 root 2. 6 root 2. So now I'm going to have here 6 root 2 I. Now, normally, again, we don't like to throw anything on the other side of the root because there's some confusion as to whether or not that I belongs underneath with the 2 or not. So just like we do with the numbers, putting the 6 in front, we will also move the I out front. So this would be the proper way to write it, 6I root 2. Although this is not incorrect, it's just not the way we prefer to write it. This is the way we prefer to write it. Again, on the next one, I drop the negative, slap the I on the outside, 90. 9 and 10. Keep that I with us. Square root of 9, 3. Square root of 10, can't do anything to it, right? None of those numbers in that list go into 10. And I still have the I on the outside. And now I'll move the I out front. 3I root 10. All right, any questions? Now for the next set of things we're going to do, I want to go back and remind you about what we had done last time. Before we got into that weird thing with all the numbers. Do you remember we were solving quadratic equations? And we were saying, okay, it's a quadratic because it's squared and then it has an equal sign, which makes it an equation. And we would do things like factoring the left side. Or in this case, we use the, remember I said it was going to take you a little time. You do like that little AC method that we went around on the board and did. Every little group did their own problem. Remember that? Set each factor to 0. Same thing here. We did that. So that's stuff we've seen. But those were all quadratic equations. Now we're going to look at a quadratic equation that's somewhat different. What if we have a quadratic equation that looks like this? A number in front of x squared plus c equals 0. So notice that there is no x term, highlighting that. What if you have no x term? I have an x squared term, don't I? But I don't have an x term. So anytime you see x squared and you see a number and you see equals, this is the method that we want to approach it with. It's called the square roots method. So the first step to the square roots method is to isolate x squared. The next thing is to take the square root on both sides of the equation. So take a look at this problem right here. X squared minus 49 equals 0. Does this look like this? Yes? What's a for us here? A is 1. It's the number in front of x squared. What is c for us here? Careful. Negative 49. Negative 49 is the c. All right? What it says is to get x by itself. So that means I want to take negative 49 and move it to the other side. So I add 49 to both sides. X squared equals 49. Next, square root both sides. Now you have to do something critically important here that you remember this. Anytime you come in and take the square root on both sides of an equation, you must include a plus or minus symbol. And then you can throw your square root on the 49. We'll talk about why you need to do that in a second. Now the reason we take the square root on both sides of the equation is because if you're saying to take the square root of something that's being squared, the square root and the squared cancel each other out, and all that leaves you with is x. On the right side, we have plus or minus, and then the square root of 49. So we do what we just did. We go over there. Oh, 7, right? 7, there's nothing left over. What does the plus or minus mean? I'm trying to solve this equation, right? Trying to find solutions. It means we have two answers, right? We have a positive 7 is one answer, a negative 7 is the other answer. And it makes sense because, look, if I say you're going to square a number to get 49, of course 7 would work. 7 squared is 49. But so would negative 7. Negative 7 times negative 7 is also 49. So we should get two answers here. And that's why it's important that we remember that when we take the square root on both sides, we must always include plus or minus. What happens if you forget the plus or minus? You've missed half your answers, right? You've missed half of the answers. All right, let's take a look at these first two are pretty easy. So let's take a look at the third one, because the third one's a little more troubling. All of these look like you have x squared. There's a number. There's no x terms, right? No x terms on all of these. How about on this? Isolate the x squared. So how do you get rid of that 25 over there? Subtract it on both sides of the equation. Now be real careful here. What do? We've isolated x squared, right? Square root. That's right. And because I'm doing this, I'm going to do plus or minus. So I say, there's a square root on the left, equals, here comes my plus or minus. And then I did the square root of the right side. But what's the right side? Negative 25. So the negative 25 goes underneath the square root. What I'm trying to get you to see is, don't let this plus or minus have any impact on that minus that's already there. That minus 25 is going underneath the square root. The plus or minus just means we're going to have two answers, a positive and a negative. Now what does the left side become? X. The right side becomes plus or minus 5i. 5i. Because we see a negative, an I pops out, square root 25 is 5. So there are two answers, 5i and negative 5i. Now let me just show you that this works. Here's the original equation, right? I'm going to replace x right now with 5i, and I'm going to show you that this is true. If I put 5i right here, I'm supposed to square it, then add 25 and get 0, right? All right, let's square this. What's 5i times 5i? Well, you square the 5. What's 5 squared? 25. You square the I, you get I squared, don't you? Plus 25 equals 0. But what did we say I squared was? It was negative 1, wasn't it? That was the big deal. The big property of I is that when you square it, you get negative 1. So this becomes 25 times negative 1 plus 25. Does that equal 0? Yes, because this becomes a negative 25, and then you add 25, that's 0. This would have also worked had you replaced it with negative 5i. See, if I put a negative right here, then when I square negative 5 times negative 5, I would still get the 25. When I square I, I'd still get I squared. So everything else would be exactly the same. Okay, look at these. Let's look at 5. Does that look like this form that we had? Do you have a quadratic equation? Yes? Okay. Is it missing the x term? Yes. Because of that, we're going to isolate the x squared. So how am I going to isolate the x squared here? Subtract 7 on both sides. This time there's a 4 over there, right? So 4 take away 7 is negative 3. Now what? Square root both sides. When I do that, I must do plus or minus. Square root of negative 3. What does my left side become? X plus or minus can you take the square root of 3? No, right? But the negative inside can pop out as a what? An I. So I need to pull an I out, and I'll still have a square root of 3, but I can't do anything with the square root of 3. So I'm going to write it this way. I root 3. Remember, you could have put the I behind the root 3, but I'm putting it in front. That's it. The answer is plus or minus I root 3. How about number 8? Is that a quadratic equation? Yes. Is it missing the x term? Yes. So the idea is to isolate x squared. This time we want to divide both sides because that's multiplication. The negative 2 is being attached to that x squared as multiplication. So I'll divide both sides by negative 2. On the left side, I have x squared. On the right side, what? 49? Is it positive or negative? Positive 49. Because a negative divided by a negative is positive. Here, now what? Square root both sides. Square root the left side, we get x. On the right, plus or minus, what is the square root of 49? It's a nice number, right? 7. So we have two answers, 7 and negative 7. Well, I like 14. That's one option. That's one option. Is this a quadratic equation? Is it missing the x term? Yes. Okay, we want to isolate the x squared, but it's trapped inside this parentheses. This 3/4 on the outside has to do one of two things. We can multiply it through the parentheses, which would release everything from the parentheses, or we can get rid of the 3/4 right now by just multiplying both sides of the equation by what? The reciprocal, 4/3. So let's do you want to distribute or do you want to do reciprocal? 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 Okay. So I'm going to multiply the left side of the equation by 4/3, which means I have to multiply the right side by 4/3. Why do we do that? Because this is going to become a what right here? That's a 1, right? Does that 4/3 have to go through the parentheses? No, that's the part that's a little tricky when it comes to the algebra. You're multiplying 1, 2, 3 things together. 1, 2, 3 things together. When you're doing multiplication, you just do 2 together. You don't distribute through multiplication. Guess what I'm trying to say is this. If I tell you to multiply 2 times 3 times 4, you don't go 2 times 3 then 2 times 4, right? You go 2 times 3 is 6 and then times 4. So Just be careful to not distribute this 4/3 through. So that's 1, which means that all you have on the left is x squared minus 17. On the right side, what is that? Is it? That's the same as 6 over 1, right? So multiply across. 6 times 4, 24. Divided by 3 is 8. Now this looks a little bit more like what we did before. Add 17 to both sides. You get x squared is 25. Square root on both sides. Plus or minus. And what's the square root of 25? 5. That all right? I'm not going to do 15, but let's talk about 15. The difference here on 15 and 14 is that on 14, there was a parentheses around these two, right? Here, there's no parentheses. So what I could do here is I could add 3 to both sides first, and then multiply both sides by what? The reciprocal of 1/2, which is 2. So this would be a different operation than this. This one, I actually do the reciprocal first, then move on. Here, I move the 3 over and then multiply both sides by 2. So there's a... If I multiply by 2, the 2 and the 2 on the 2 would be like a 2 on top, and then cancel with the 2 on bottom. It would just become x squared. We're not in any hurry, right? You go to that point, then you multiply 2 here, 2 here. These cancel. X squared is equal to 64. Oh, how nice. X equals plus or minus 8. I'm not showing the square root step anymore, assuming that you've kind of picked up on that. All right, so we've been very careful to avoid quadratic equations that have x, right? An x term, everything we've done here is if it doesn't have x. Well, what if it does have an x term? Okay, so this is where the good old quadratic formula comes from. Anytime you have this equation, so if anyone ever gives you an equation where you have an x squared, you have an x term and a number, and this formula is so powerful, it doesn't even matter. You can be missing an x term and this formula will still work. So this formula works on all the problems we did up here. It works also. But this is quick and easy to do. And this c can actually be a 0 also. So you could have a mixture of no x terms or no constants, as long as it's quadratic. In other words, as long as you have an x squared here and it's an equation, this formula is valid. And here's the formula. The solutions to this, the solutions will be x is negative b plus or minus square root b squared minus 4ac goes under the root, all divided by 2 times a. How many of you have seen that formula before? Yes? Okay. One of the more famous formulas in math, right? Very powerful. It allows us to solve any quadratic equation. I wonder, you probably don't, but if this is a quadratic equation, highest power of x we see is 2, right? This is a formula for solving any quadratic that looks like that. What if the highest power on x is 1? Isn't that just a linear equation? And we're all pretty comfortable solving linear equations. You just isolate the x, right? Like if I had 3x minus 7 equals 10. If I said solve for x, you think you can handle that? Move things around? So solving equations when the highest power on x is 1 is relatively easy. When the highest power is 2, it can get kind of tricky, but we have a formula for it. What if the highest power is 3? You think we have a formula? What do you think? Yes? No? Yeah, it's about half a page long, though. It's not a formula you would ever memorize. And how about if the power is 4? It's several pages long, actually. I wonder if we could look at it. Y'all seem like y'all want to look at it right now. Cubic equation formula. There it is. So here's the formula for a quadratic, right? You've seen that? Here's for a cubic. Oof. What a disaster, right? Imagine having to memorize that for a test. And then I believe for 4th degree, let's see. Huh? Are they explaining it? Yeah, you know, it's very difficult to generate that formula. 4th degree equation formula. Let's see if we get quartic function. Is there a general formula? Oh, here we go. Well, will you just trust me that it's a monster? I don't see it here. You trust me that's a monster? But what's interesting is this. 5th degree and higher, no equation exists. That doesn't mean we haven't found it. It's actually been proven it doesn't exist. There's a difference. It's like me saying there are no red fire trucks in this room, right? There's a difference between me saying there's none because I haven't found one versus I've gone through the room, there are no red fire trucks in the room. You know what I'm saying? There's a difference between those two things. So we've proven that after 4th degree, there is no formula. But unfortunately for us, for 2nd degree, there is, and we have to know how to use it. All right, so let's take a look at, let's do number 2. I recommend you get your calculator out if you have it, because we're going to get what's called the exact answer, and we're going to get what's called the approximate answer, both. So take a look at this equation right here. That's negative x squared plus 12 equals 9x. I want to make that look like ax squared plus bx plus c equals 0. Notice we have the x term in there now, right? So we can't do what we just did. Doesn't work that way. If the x term's in there, it throws everything off. So you get to choose here to move everything to one side of the equation, because the important thing for quadratic equations is that one side must be 0. So your choice, you want everything to the left or to the right? Both ways will give you the same answer. You just want to move the 9x over to the left. Okay, if I move the 9x over to the left, it's going to become a negative 9x, right? And let's put this in order. We call this, what order? Do you remember? What's that? Descending order, yes. We always want to write it highest power of x down. So we had the negative x squared here. The negative 9x came from the other side, and then positive 12. Let's identify a, b, and c. A is the number in front of x squared. B is the number in front of x. and C is the number by itself. So A, B, and C are always numbers. A, B, and C never have X in them. So when you write down what A is, it's just a number. B is just a number. C is just a number. So tell me what A is here for us. What is it? -1. Right? It's the number in front of x squared. It's not -1x squared. It's just -1. What's B? -9. What's C? 12. So you got to make sure you keep the sign of what they are. Right? Now, I would like for you to see if you can plug that into the formula. So I'll write the formula. I'm going to write the formula on the board so we can refer to it. And I want to see how you all do with the formula on your own before I do it. Make sure you put that x equals out front. See what you come up with there. I'll be right back. everyone had a chance to plug it in and you think you have the right answer? Okay, let's see. So the first part of the formula, negative b, that will always be the opposite of the b that you see here, right? Because you're going to make a negative or change the sign of what's here. So what am I going to put here? 9 plus or minus square root. What do you think the plus or minus is going to do? Give us the two answers, right? Quadratic equation, we should get two answers here. All right, the next number inside the square root, the first thing is b squared. Won't that always be a positive number? Yes? It'll always be a positive number because you're going to be squaring a number. And it's never going to be, this is never going to be an imaginary number because we said for a quadratic it has to be in the form, where did I put it? Here, where all these are numbers. I should have put real numbers, not imaginary, but okay. So square b, and what do you get? 81. Minus 4 times a, what's a? Negative 1 times c, which is 12. The entire thing, everything, all the way across. 2 times a, which is negative 1. All right, now here's the way I recommend you do this inside part, because this is the part that gets most people. When you're going to figure out all this, figure out what these three numbers multiply to be first. All right? And don't worry about the minus sign right now. Just what's 4 times negative 1 times 12. So what is 4 times negative 1 times 12? Negative 48. Do we all agree with that? Those three numbers in yellow are negative 48. So what you have here is 81 take away negative. What does taking away a negative really mean? Adding. Right? Double negative becomes a plus. So I'm going to say that this is equal to 9 plus or minus the square root of 81 plus 48 all over, I'll just multiply the bottom negative 2. Is that all right? What is 81 plus 48? What is it? 129. All right, so 9 plus or minus the square root of 129 all over negative 2. Good. Now, can we break 129 down? This, not with a perfect square, right? It does break down. There are some numbers that go into 129, but none of them are perfect squares. And you would just have to work through that on your own. If it did, you would have to simplify it. This right here can't be simplified. So at this point, we're done. This is what we consider to be the exact answer. This is the exact answer. Now, if we want the approximate answer, which we need to know how to do, what we're going to do is we're actually going to get on our calculator, and we're going to take the square root of 129 on our calculators. I'm getting 11.35781669, something like that. Let's just round this 2 decimal places. So this will be equal to 9 plus or minus, what should I write now? After the plus or minus. Do I write the square root? No, because I'm taking the square root, right? So I just write the number I get on my calculator, 11.36. That sound okay to you? All right, over negative 2. And now we actually have to figure out what these two answers are, because there's two answers here, right? 9 plus that number, 9 minus that number. So I'm kind of out of room, but here's the way I like to write it. I like to say equals, and then I like to do 2 different scenarios. So I do like 2 arrows coming off of this. Here's what's going to happen if I treat it like a plus. When I say it, I'm talking about this, plus or minus. First, top one is going to be if it's a plus, the bottom one's going to be if it's a minus. So if I do plus, I'm doing 9 plus 11.36 over negative 2, which means I first add these together on my calculator or in my head. What is 9 plus 11.36? What is it? 20.36 over negative 2. And now do that on your calculator. What do we have? 10 point, negative 10, sorry, negative 10.18. That is one answer. The other answer is what happens when I do the minus between them. 9, take away 11.36, and divide by negative 2. This time, I get negative 2.36 over negative 2, which is what? 1.18. Positive, right? And so we have 2 answers. All right? That's the way we solve a quadratic equation using a quadratic formula. The good thing about the quadratic formula, it always works. The bad thing, it can take some time, and there's a lot of room for error because there's, you can miss a sign or something like that. But it's, it's the ultimate weapon against quadratic equations. Yes? It depends on if you type it in correctly. So depending on your calculator, do you have your calculator right there? What, can you hold it up? What kind is it? Okay, so you would need to use parentheses. Yes, as long as you're using parentheses properly, you could. Yep. Like on that top one, just for everyone, you would, if you're using a calculator, most of you have a calculator like this, you go parenthesis 9 plus 11.36, close parenthesis, then divide, and then here you use the little negative symbol too. If you do it like that, typed in, it'll work. If you do not put those parentheses around there, your calculator will actually do just the 11.36 divided by negative 2 first, then add 9. That's completely wrong. So you just have to be careful with that. All right. Let's look at number 4. I've kind of used up a lot of space for 4, but let's do that right here. X squared minus 3x minus 5 equals 0. So what have I done already to start off? Subtracted 6 from both sides. That way I can get it to be equal. Now, if I'm solving quadratic equations, right, the first thing I'm looking for is, do I have an x term? Which I do, so I can't use the method we just did before. But before I do quadratic formula, I always ask myself whether or not I can factor this. And what I mean is using that little thing over here and coming up with the 2 numbers, right? That thing that we did in class before. But if you do this method right now, you'll soon find that you cannot factor that. It just won't work. There's no numbers that you can come up with that'll actually do what you need them to do. So because that fails, you really have nothing else but the quadratic formula. All right, so let's identify A, B, and C. A is 1, B is -3, and C is -5. Okay, good. Now, right into the formula. X equals, what's negative B? 3 plus or minus the square root. What's B squared? 9 minus 4 times A is 1, C is -5, right? All of this over 2 times 1. I want to see if you can tell me what is under that root. Oh, how many of you had gotten this correct over here? How many of you had gotten that right? Yeah? Okay. See if you can come up with the number underneath. That is the biggest issue I see with quadratic formulas. People are have trouble getting all this to be put together properly. What's under the root? 29? That is correct. 29. Multiplying 4 times 1 times -5 is -20, but then you're subtracting -20. So it adds. So 9 plus 20 is 29. And then all over what? 2. Does root 29 break down? No. So that would be your exact answer right there. And then you could go on and get the 2 decimals. I'm going to say ... I'm not going to go through that right now. Everybody get the idea? Okay, what we're going to do now is we're going to get you started on your homework. Let me see if I can get to homework. There we go. Okay, what I'd like for you to do is I'd like for you to pair up 2 people per group. I'd like for you to not write anything down on your paper. I want every pair to go to a part of the board, and then I'm going to give you which problem that you're going to do. And y'all are going to work together and talk to each other and work on the board and try and work through the problem I give you. Sound fair? Okay. So this is kind of random. Everybody got their group? Everyone ready? You're going to do number 13 on page, I don't know what page that is. It 28? Yeah, 13 on 28. Are we off by one? Are y'all going to go? Yes? Okay. You're going to do 15. Okay, so that's this one on page 28. 2 there? Yes? That one has a decimal. I'll keep you away from that. How about 17? What would you do if you had a decimal, though? Skip it, right? No. You would need to get this decimal to not be a 10.3, move the decimal over, right? But you have to do that to everything. So this would become a 160, this would become a 103, and this would become a 20, and that would be big numbers. But that would be life, right? Sometimes life gives you that. Okay, I'm going to go over here now, right here, this pair. 18 here, and let's do 20 back there. Okay, 18, 20. 22. And I'm all out. No, I have more. Huh? You want to do the decimal one? Okay, then why don't you do number 14? Okay? Yeah, and put what number what I gave you up there somewhere. Like if I gave you number You've got yours, right? We still need another group? Okay. I'm trying to see what I've already assigned. I gave 20. Did I give 21 to anyone? No? Try 21. Okay? Spread yourselves out. Oh, erase. Yeah, we can erase all that. And if need be, I've got this thing works pretty good. Oh, don't use your hand. Don't use your, here. And turn red. Does everyone have markers? Okay, so with what we've done, hopefully you can get your homework for this section done. There was one problem over there with the decimal that looked like a monster. I do want to check to see if that came out to be correct. Not because I'm checking their work, but it's something I don't feel like looking at. So I think what I'll do is I'll go to Wolfram Alpha, which is that website I think I've shown you. And what did you have? 5220x squared. And then what is that? Minus x. And then I would type equals 0 and enter. Let's see what it comes up with. All right. 10 over, let me see. They probably have decimal answers somewhere here. No? Approximate forms. They're getting 0.85 and 0.344. So there's something off. When you squared the negative 2637, did you make it positive? I think that might be the problem. You kept it negative? That's the problem. Remember that on the b squared, even if it starts negative, when you square it, it's going to become positive. That's probably the mistake. Okay, so the purpose of this was just to, again, illustrate you've got to be careful with all these little signs. Keep track of everything because, you know, when I grade these, I'm grading them for correctness. You know, I mean, it's a formula. What you're being tested on is, can you apply the formula properly? So keep that in mind. Okay, now the purpose of everything we've done with the solving quadratic equations was to get us prepared for looking at now what are called quadratic functions. So remember that we had these things like f of x equals 3x plus 1, or we would write something like this, y equals 3x plus 1. And if I asked us to graph this, what was that when we graphed this? It was a straight line, wasn't it? And it was very easy to graph because all we had to do was identify the y-intercept and then the slope. And we went around the board and we did that also. Remember, you graphed the point, put the y-intercept in up 1, you know, over 2, or up 3 over 5, whatever it was. So graphing lines, relatively simple. But if we now change this function, f of x, and on the right side we don't put a line, we put a quadratic, then the picture is very different. And all the quadratic functions have similar properties. And so that's what we're going to go through, is talk about the key elements of a quadratic function. So first of all, the standard form, what we call the standard form of a quadratic function, is written, it's up here, but I'll just write it to the side also, is any function f of x equals ax squared plus bx plus c. So the ax squared plus bx plus c should look very familiar because that's what the quadratic formula required, right? but we set it equal to 0, right? We're not doing that right here. We're just writing it out as an expression. You could also look at the left side as being y equals ax squared plus bx plus c. But remember, by putting f of x, we're telling you it's a function, which means it passes the vertical line test. So for each of the problems that we're going to do from here on out, we're going to be asked to graph this quadratic function. These are the things that you'll be asked to find for each of the quadratic functions we graph. Something called the axis of symmetry. You'll be asked to find the vertex, the direction the graph opens, the x-intercepts, the y-intercept, and the domain and range. So I think the best way to kind of get started with this is to get me to a new page so I can kind of introduce this a different way than they do. So if you're given this function, there's one of two possibilities is in terms of the picture. You could have this possibility, first one, that it looks like a U, kind of like a smiley face, right? We call this a parabola. And in this one, we would say that this one opens up. The way that you can determine whether or not a parabola opens up or down is by simply identifying one number, and that's a. It will always open up if a is bigger than 0. So if the number in front of x squared is positive, you're guaranteed the parabola opens up. Looks like a smile. The other possibility is that your parabola opens down. So it looks like an upside down U. We would say that this one opens down. And again, a will dictate whether or not it opens up or down. And in this case, a would be less than 0 or a negative number. So positive people smile, negative people frown, right? What do the arrows at the end of these parabolas mean? What are the little arrow here and arrow here? It keeps doing that, right? So this parabola opens up, keeps going up and to the left forever. This one goes up and to the right forever. Same thing here, same thing here. What about on both of these parabolas? Let's just quickly talk about domain. What would the domain of both of these be? All real numbers, right? Because look, if you move to the left, the graph is always there, right? You move to the right, the graph is always there. So you always have graph as you move out left and right. And that works for both of these. Range, on the other hand, is a little bit different. On the range for this parabola, doesn't it have a lowest point? But it has no highest point. So the range is always going to go from some point up forever. On this one, the range is always going to go from, what, way down there forever, up to a highest point, right? We'll just keep that in mind. We'll actually, when I give you a specific example, we'll actually find the domain and range. But the domain's always going to be easy, everything, right? All real numbers. Range will always be one of two different cases. All right, so this is just to show you what they look like and how A dictates the opening of up and down. Now, the next thing I want to look at is, so this is kind of a separate topic, is that in either case, right, whether or not it opens up or down, you will have a point, which is very important on the parabolas. In the case that it opens up, it's the lowest point on the graph, isn't it? It's the lowest point. This is called the vertex. On the parabola that opens down, that point will correspond to the highest point on the graph, right? So you're either going to have a lowest point on the graph or a highest, depending on if it opens up or down. This point is so important that we actually give it a special x and y coordinate. We don't call it x and y, we call it h and k. And this one also would be h and k. And there is a very nice way to find the vertex for any parabola. Right? We have a very nice formula which allows us to compute those two values, h and k, very quickly. Well, I don't know about quickly, but easily. So we have what's called the vertex formula. And we aren't here to talk about where it comes from, all right? You go take a Calculus 1 class, and then you talk about where it comes from, but not here. So I just give it to you. H is equal to negative b over 2a. Always, okay? Always. If you want to know this point right here, this x value of this point, all you have to do is figure out what negative b over 2a is. And remember on our quadratic formula, remember this over here? We have negative b plus or minus all this junk over 2a. That formula is almost this formula, but all this junk is not there, right? Take all that junk away, just do this divided by that. That's going to be the h all the time. The k, though, is a little more tricky. The k is f of h. What do I mean by that? Yeah, you plug the value you get here, whatever this number is, you figure it out, you plug it back into the function, whatever was given to you, whatever that spits out is your k. So that means if you get h wrong, guess what else is going to be wrong? K is going to be wrong also. So you got to be real careful that you get h correctly. All right, so right now, someone gives you a quadratic function. You should be able to determine if it opens up or down pretty easily by just looking at a. And you should be able to tell me what the lowest point is if it opens up or the highest point if it opens down. Yes? Okay, the next characteristic of a parabola that we're interested in, and this one actually isn't used a whole lot, but it's good to know what it is. Let me put the vertex here again. This next one is called the axis of symmetry. Is that right? Symmetry? Doesn't look right. Okay. There's a reason why I'm not an English major. Like I was never an English major. The axis of symmetry is always an imaginary line. It's not part of our graph, okay? Our graph is what's drawn there in red. But this imaginary vertical dotted line is called the axis of symmetry, and they call it that because if you were to take this left side and mirror it over that line, reflect it, it would just go and lay right on top of the right side, right? So it'd be like a mirror image or a reflection. It is symmetric to that line. And that always has an equation. Remember, vertical lines have an equation. Vertical lines, the equations are x equals some constant. In this case, it will always be h. It's always the x coordinate of your vertex. This is the equation of the line, which is your axis of symmetry. X equals a number. Yep. All right, so that's your axis of symmetry. We have the vertex. Now let's talk a little bit about intercepts. Intercepts, remember, are wherever the graph hits the axes. Let's start with x-intercepts. When it comes to x-intercepts, we're saying where does the parabola hit the x-axis, right? There are three possible scenarios that we could have. you could have a parabola that hits the graph, hits the x-axis in two places, right? Does that make sense that you could have a parabola that does that? Yes? And that means that if I went to go find the x-intercepts for that parabola, I should get two answers. Yes? Does anyone remember how we find x-intercepts? We set y equal to 0, didn't we? To find x-intercepts, you set y equal to 0. Wouldn't that mean the same as doing this? Here's the function. We would say y equals this, right? But if we want to know the x-intercepts, we're replacing y with 0. So doesn't it turn into this equation? And isn't that what we use quadratic formula on? So the quadratic formula is what supplies us with the x-intercepts. And we saw from around the boards, we could get two answers, right? We also said we could get one, didn't we? So what would the graph look like if I only had one answer? That's right. The vertex, right, would actually sit on the x-axis. So this is the case where you would have, so one answer here, one x-intercept. Here it was 2. And is it possible to have a parabola that has no x-intercepts? Sure. What about the one that looks like this? Right? That never hits the x-axis. And which of these cases on the board do you think that is? That one. Square root of negative 47. It spit out an imaginary number, didn't it? Whenever that happens, you know your parabola never touches the x-axis. Make sense? So this, no x-intercepts at all. Now, I want to go into this a little bit further. Let's look at this example over here on the board. I'm sorry, I'm going to reach over you here. On this example, when they did all the work, this square root, right? B squared minus 4AC in the formula. When they did B squared minus 4AC, they got square root of 961, which they got on their calculator, and they got an answer, right? Square root of 961. And so they're going to have plus or minus some number, aren't they? That's going to give them two answers. In the next problem, same thing. Underneath that square root, they had a 109, which means they're going to get two answers also, right? The problem number 22, what did they have under their square root? 0, which means plus or minus doesn't matter, because when you add or subtract, nothing doesn't change. That's why they got one answer. And over here, with the negative under the root, that means they had an imaginary number, which means that the part that's underneath the square root dictates how many answers you get. It completely controls it. And that's why that thing underneath the square root is so important to us, so important that we give it a name. It's called the discriminant. And what it is just the b squared minus 4ac. Tell me now, with this case where you have two answers, what must the discriminant be? In order to get two x-intercepts, your discriminant is going to have to be what? Positive, right? 961, 109, right? 17. So what we say is in this case, your discriminant, I'm just going to put discrim is positive, greater than 0. Do you all understand what I mean by that? The discriminant must be positive. The thing underneath the square root must turn out to be a positive number for you to have two answers. What about with one answer? What does a discriminant have to be? Over there, 0, right? You must have a 0 underneath the root. And then to have no solutions, what must the discriminant be? Must be negative number, right? Less than 0. which would force you to spit the eye out in imaginary numbers or live in a different fishbowl, right? That's what we talked about last class. So the discriminant is a very powerful thing. If you know about the discriminant, you know a lot about what your graph looks like. All right. So when it comes to x-intercepts, there's three possibilities: two, one, or none. What about y-intercepts? That's where the graph hits the y-axis, right? If I draw a parabola, how many possible y-intercepts can I have? Just one. I don't care how you draw your parabola. Open it up or down, doesn't matter. It can only hit this once, right? What if I try and move my parabola way over here? So I'm like, no, it doesn't. Look, over here, this parabola doesn't hit it. It will eventually. It's going to go up and over, right? There's no stopping it from moving. You'll hit eventually. But can you hit it more than one time? No, because then it would fail to even be a function, because it would fail the vertical line test. So with the y-intercept, you always have one. And how did we find y-intercepts? To find the y-intercept, you replace x with 0. So all we really have to do is this to find the y-intercept. Plug 0 into the function. Whatever that is your y-intercept. That's usually very easy to do in a quadratic function. Plug 0 in. It's harder to get x-intercepts than it is y-intercepts. All right, so we are about to go try and graph these things and figure out all this information, you know, vertex, x-intercepts, y-intercepts, domain, range, axis of symmetry. But before I do, I just want to talk about why parabolas are actually useful. And there's not a whole lot that I can do in this class that I can convince you that this stuff is actually worth doing. So let's take a look at something. I'm going to do this as a visual example. So let me see, grab this here. See, I'm going to grab another marker. You're good. All right. All right, you all ready? I'm going to throw this over there. You ready to catch this? I'm trying to do a good throw here. So I'm going to throw this through the air. I just want you to watch its path. You know what? This will be better. Okay. You mind going over there? So I want you to watch the shadow of this thing across the board. Sorry, it's a bad throw. This one's going to be short, all right? So don't worry. Throw it back to me. Throw it back to me. Okay. So watch this one. You won't be able to catch this one. Okay. So that's good. If you launch something through the air, right? Throw something, a ball, whatever. As soon as you let go of it, it starts traveling up and then it comes back down, right? The path that it travels through the air is a parabola. All objects on any planet with gravity must have a parabolic path through the air, right? And we figured that out a long time ago. So let's say that I've figured out that all objects travel through the air in the shape of a parabola. And let's say that there's a castle over here that I wish to go in and steal all their shit and kill the people I don't like and take their money and eat their food, right? I want to conquer them, right? Because men, mankind, we like that, right? We like doing that sort of thing. So one approach is to just lob shit at their castle all day long, right? And hope to hit them. Or possibly, if my brain is advanced enough, if my civilization is advanced enough, I actually understand there's more to just lobbing things through the air. And if I know that, they keep all their supplies in this corner, and I'd like to hit that, right? And I know that all things travel through the air in the form of a parabola. And let's say, I'm over here on a hill, then what I really would like to know is an x-intercept, right? Imagine now that this graph, somehow we have you can almost look like an xy axis here. There's your parabola. And what I really need to discover is the x-intercept, right? The x-intercept of this graph. And so what I've done is, before I got to the castle, I said if I have this cannon with this sort of, pack it with this sort of powder and, put this size ball in it, I go test it out in the field. I know that if I aim it a certain way, it's going to be a certain shape, and I know exactly where it's going to hit. And then it's not just throwing stuff, right? I mean, there's some thought to it. If I want to take out this, I know what to do here, right? I know how to change things. But you have to understand how the parabola works before you can do that, right? Now it's a little different, right? Now you just type in GPS coordinates and let it go from, 100 miles away, and it goes and finds it and blows it away. But that's an advancement, right? That's an advancement. This technology wouldn't hold up in warfare anymore, would it? But that's where it starts. So there's a parabola. That's one example of a parabola. Let me give you another example of a parabola. Anybody here drive a car that has headlights? Yes? We all have headlights, right? I mean, I'm trying to make a point. We all drive a car, right, that has lights. Okay, when you turn on your lights in your car, you get a beam, don't you? A beam of light, especially if you do your high beams. I mean, if you've ever driven through like fog or something, you can actually see the beam of light coming out of the front of the car. The way that a headlight works is as follows. It has a bulb. Okay, and this bulb shines light, right? And when you turn on a light bulb, light goes in every direction, doesn't it? Off that bulb, it goes in every direction. So how do we focus it into one place? What we do is we place behind the bulb, and this is like a side view of this, we place a mirror. And that mirror that goes behind it, okay, we want to keep in mind the front of the car is aimed that way, all right? What happens is that as the light comes out of this, it bounces off the mirror and goes out, right? It's going to bounce and go out. If I change the shape of this blue thing, it's going to change where that light reflects, like how it comes out, right? It turns out that if you use a parabola, okay, this is a parabola, it's just sideways. If you use a parabola, then what it does is it forces all of the light beams to come out straight, like this. This mirror in the back can't just be just throw some curved thing back there. No, it has to be parabolic. It has to, in order for the light to come out in a beam shape. All right? This point right here, where you position the light bulb, is called the focus. Now, have any of you ever used a flashlight where it has, like, you twist it and it changes the beam? Right? It's like it's real narrow, and then you twist it and it goes, whoa, and it widens out. All you're doing there is you're moving the mirror backward and forward. And if I move it backwards, what happens is I change what happens. I move the focus, and things don't come out in a straight line anymore. They come out all skewed out like this. So maybe that will come out like that now. That one will come out like that. You know what I'm saying? It spreads the beams out. It's not as bright because it's spread out. But all I've done is I've changed the position of the parabola. So you can't do that without a parabola. Right? If I'm manufacturing headlights, I better know something about parabolas, or else I can't do it. Any of you that watch TV or use cell phones, you might appreciate this. You've seen these on the sides of houses or up on their roofs, right? These little satellites they have, right? DirecTV. But even like the major TV stations, right? Even like Time Warner and stuff like that, they do communicate not just with cables, they use satellites. So this is what we consider a satellite dish. And the way the dish works is the opposite of the light of the headlight. What happens is you've got this dish. Let me make it a smaller dish. You've got this dish sitting on your house. There's your house. Okay? There's your house. There's your dish. Big old dish. That's like the old days, right? Have you ever seen those dishes that are like in the back of people's yards, like poured in concrete? They're like, 28 feet long or so. I mean, that's the good old days, I guess. Right now it's all like this little thing. Okay, so what happens is I want to get a TV show, right? There's my house sitting there. Now let me kind of zoom out. Here's the earth. Here's my house. Here's my dish on the house. And I want to communicate with someone else over here on the other side of the world, right? Well, I cannot, even if I send out a signal out, they're never going to get it because the Earth's in the way, right? The Earth is in the way of my signal. So what we do is we send up a satellite that has a dish on it, and when I send out my signal, that dish collects my signal and then sends that signal back out to other people over here, transmits it out, and then they can catch it with their dish, right? That's how you get around the world and not, get the Earth to not block you anymore. But the actual collection of that requires a parabola, because when you focus in on this dish, and let's look at that dish from the side, it's sitting out there and they say point it at a certain place in the sky, right? If any of you have ever set up a DirecTV or something like that. And all it's doing is it's grabbing this very, very weak signal. It's a weak signal because there's a lot, it's spread out everywhere. And what it does is because it's a parabola, it's reverse of the headlight, it sends everything back to that same point on the dish. And that amplifies the signal. It's like turning the volume up by focusing it all on one point. If you've ever used a magnifying glass to burn bugs, I'm kidding. I've never done that. I've set leaves on fire. But you know what I'm saying? It's that process of focusing everything into one place. Then that goes in, it goes to a cable, goes to your TV, and you watch TV. Or you talk on the phone. Same thing. You must have parabolas for this to be able to work. All right. Well, I was going to share one more thing with you while we're talking about Earth. These satellites, right, are sitting there up in space, right? Doot, 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 and they're going around the Earth or something like that, right? Okay, so how do they keep going? Like, don't they run out of gas or something eventually? It's orbit? What's orbit? I mean, I don't understand. They're out there. Why aren't they falling to the Earth? I don't get it. But see, gravity is inversely proportional to the square of the distance. That's technically the way you say it. There is gravity. The further you get away, the weaker it becomes. But the satellites are still within the gravitational field of the Earth. I mean, they still do feel gravity. So why don't they start coming back towards the Earth, right? Why don't they actually start falling towards the Earth? Yeah, why doesn't it? Okay, so that's why I want to bring this up. This is way off topic, but okay, so let me go to another analogy for you. Let's imagine you're standing here. Again, my artistry, I'm a little bit conceited when it comes to my artistic ability, okay? Oh, don't deny how good it is, okay? That's a gun, okay? Well, it's a big gun. I shoot a bullet, right? I shoot a bullet straight out of the gun. What happens to the bullet? It's going to start going down, right? That's actually going to be parabolic, but it's kind of beside the point. It's going to hit the ground, right? Now, if I shoot the bullet even faster out of the gun, it's just going to go further, right? But it will still hit the ground. And it actually turns out that it'll hit the ground at the same time. Those two bullets would hit the ground at the exact same time. It does not matter which one's going faster. They both fall and hit the ground at the same exact time. So if I drop a bullet and I shoot a bullet, They both hit the ground at the same time. All right? That was my that's if you're on a planet without air. Yes. Yes. Okay, we can get to that later. Now, it's going to fall, right? It's going to start falling. What if I shoot it so fast? What if I shoot this bullet so fast that, well, we know that the Earth is curved, right? What if I stand here and shoot my bullet so fast that as it falls, the Earth curves away from it? So it's moving so fast that it's trying to fall, but the curvature of the Earth is actually falling, curving away from it as it falls. So it's just continuously falling. That's what a satellite is. It's sent out into orbit at a certain speed so that, and they calculate all this, so that they get it up there to the certain speed, certain altitude, they cut the engines, and now it's falling towards the Earth, but the Earth is curving away from it. And it's continuously falling towards the Earth as the Earth continuously curves away from it. It just keeps doing that perpetually. And that's exactly what the moon is doing to us. Everything is stuck in a fall. So when you say like the moon is the Earth, well, we're not good enough. We get it so close, but like, after a while it gets a little bit off, and yeah, they'll angle it back in and they'll crash it into the atmosphere and it'll rip itself apart. Okay, so I've always thought that was pretty interesting. It's like it's not actually just sitting up there like hovering, or it's falling. And there's also satellites that are called geosynchronous satellites, where what you do is you get it up there and it's falling, but you get it to a certain altitude where as it's moving, it's in sync with the speed of the Earth's rotation. So the Earth is rotating, right? The Earth is turning as it's moving. And if you get it just right, that satellite will stay over the same spot all the time. So I'm falling towards the Earth, but the Earth is turning, and I'm falling, and I'm turning, and I'm always over the same spot on the Earth. And that's called geosynchronous orbit. So you have the same satellite above you all the time. I'm sure that the military has plenty of those that we don't know about, sitting over us all the time, watching. I hope so. It'd be nice to know that they are watching us that well, right? Okay. Wow. Getting back to the fun stuff. Let's get back to this stuff. All right. So let's take a graph. Let's actually graph one of these. I want to get down to business here. We'll start with number 2. I'm going to do this on a separate piece of paper. X squared minus 6x plus 13. This is our function. Now, as long as I've been teaching, most textbooks have a certain way that they encourage students to graph quadratic functions. And there's nothing wrong with that method. I'm not here to say it's bad or wrong, but I kind of always have had my own way of doing it, and I think it's more efficient. So I'm going to just show you the way that I do these, all right? The first thing I'm going to do is I'm going to make sure it's a parabola, or it's a quadratic function. And the reason why I want to make sure it's a quadratic function is because after we study quadratic functions, we're going to study polynomial functions, and after polynomial functions, rational functions. And they all have very different approaches when it comes to graphing them. So I got to make sure I know what I'm looking at is a quadratic, so that I can talk axis of symmetry and vertex and all that. So check that first. Is this a quadratic function? Yes? Check. Okay. Second step, does it open up or down? You're saying up? Why? Because the A, right, A is 1, and that's a positive number. A is the number in front of x squared, right? That's your A. In fact, let's just write down A, B, and C, because we may need all those. 1, negative 6, and 13. Y'all really don't think that my art's that good? I mean, you take a class. I'm starting to feel a little bit self-conscious about it now. All this time I thought it was great. So it opens up. All right, I'm going to draw a little picture of this. It opens up. Keeping that in mind, I'm going to even draw a little vertex on it because I know it's going to have a little vertex, right? Somewhere. The next step is actually to find the vertex. Find vertex. How do we find the vertex? It's a formula, right? H equals negative B over 2 times A. And for us, that would be what? What's negative B for us? Positive 6, right? Change the sign. Over 2 times A is 1, so we get 3. So H is 3. And how do you find K? Plug 3, the answer we just got, into the function. And that means you actually have to go and plug 3 in. It's, you know, just take your time. I'm plugging it into this right here. So I'm going to be doing, what, 3 squared? I don't need the parentheses, but I'm going to put it anyway. Minus 6 times 3, then plus 13. So 9 minus 18 plus 13, 4. So the vertex is a point, and we just found the vertex to be the point 3, 4. So I could actually go graph it now, couldn't I? I know exactly where it is. Y'all still with me? The fourth step, and this is where my way kind of deviates from most textbooks. I like to do what's called a quick sketch here. A quick sketch. All I want us to do is draw our X and Y axes, place the vertex on the graph, very rough sketch, 1, 2, 3, 1, 2, 3, 4. There's our vertex. And then from this, I want us to use the fact that it opens up or down to kind of just draw a picture of kind of what it looks like. So what does this, which way am I going to draw this? Up, right? Because it opens up. So that's, because it opens up, the vertex is the lowest point on the graph. And you go like this. See that? Now, from this quick sketch, can you tell me what the axis of symmetry is? It's just that dotted line that goes up the middle. And we said the axis of symmetry will always be what? X equals H, which in our case will be 3. So the axis of symmetry is X equals 3. That's our axis of symmetry. Y'all okay with this? All right, the fifth step in the process that I like to use is a question you ask yourself. Do you have x-intercepts? If so, solve ax squared plus bx plus c equals 0. Right, that means we set the function equal to 0 and solve. What if we don't? We just move on to the next step. If not, move on. So I was saying step 4 and step 5 are kind of something that I've always done that a lot of textbooks don't do. Do you see why I do that? Do we have x-intercepts here? No. So why in the world would we go spend the time of trying to solve this quadratic equation when I know that I'm going to get a negative discriminant and a negative number underneath the root? I already know that because I can tell by my picture. So why waste my time going and doing this? Do you see what I'm saying? So we can skip that step completely. Now, had this parabola opened down, then of course we would have to do it, and we didn't save ourselves any time. But in this case, we did. So we do not have x-intercepts here. So in this particular problem, I'm moving on. And now step 6, the y-intercept. Are we going to have a y-intercept? Always, right? We said we'll always have one. How do you find it? Plug 0 into the function. Always. So plug 0 into our original function. That's this one. What do you get? 13. So as a point on our graph, it's actually the point 0, 13, isn't it? It's the point 0, 13. From here, we can draw the whole graph, right? We've got everything we need. So step 7 is going to be to do our final sketch and then state the domain and range. Final sketch. State domain and range. You don't need graph paper to do this. If you want to use graph paper, you can. I'm not going to tell you you can't, but it's not required. Now notice that my graph is mostly up above the x-axis. That's because I know that this thing opens up and I knew where my vertex was from my quick sketch. I'm going to go to the right 3. Was it 3, 4? Up 4. So remember, I need to go all the way up to 13, though, on the y-axis, don't I? Because my y-intercept. So I want to make sure I give myself enough room. 1, 2, 3, 5, 6, 7, 8, 9, 10, 11, 12. There's 13 right there. 1, 2, 3, 4's right here. 3's right here. Here's my x-axis. I'm going to draw my vertex at 3, 4. That's one point that I know lives on my graph, right? That's one. The other one I know is up here at 0, 13. I know that I have like this imaginary vertical dotted line, which means that it's a reflection over that line. And I know it looks like a U. So I'm going to do my best here to draw a U on the right side. Oh, man. Come on. There we go. All right. There. It doesn't have to be perfect. And then try and kind of replicate that on the other side. Like you don't want to do this, right? You don't want to be like, there's my parabola. You want it to make it look as symmetric as possible. Something like that. That's decent. That I can take. You don't need to put the mirrored side on there. That's okay. If you want to, you can, but you don't have to. All right? That's it. That's the sketch. Now, what's the domain? Everyone should get this right on the test. Negative infinity to infinity, or you could say all real numbers. What's the range? This is the part that you have to, what's the range? Range are your Y values. 4 is the lowest Y value you have, isn't it? When it comes to Y values, 4 is the smallest Y value you have, and then everything above that, your graph exists. So you should have a range from 4 to positive infinity. Now, if you really want to get particular, you could label your axis of symmetry x equals 3. You could label your graph f of x equals x squared. What was it? Was it minus 6x plus 13? Right? And that would be a pretty decent graph there. You could go as far as labeling your vertex 3, 4, labeling this point 0, 13. As much detail as you want, but what I need to be able to do is on a test just see that you got the information the correct way, and that there's enough on your graph for me to conclude that you have the correct vertex and have the correct y-intercept. What I don't want is something like this, what that would tell me is that you used your graphing calculator, you typed it in, and that's what your graphing calculator told you. Because your graphing calculator, I know, is already preset for a window where it doesn't go up to 13, so it wouldn't have shown the y-intercept. And there's no detail on this, all right? I don't want that. I want the process and the steps to be shown. Okay? All right, you ready to do one on your own? Of course you are. You're excited about it. Please follow these steps, all right? 7 steps. All right, I'm going to give you one, since this is your first one. I'm going to give you one where all the numbers work out nice, like everything's going to be nice. I want you to follow the 7 steps to sketch f of x equals x squared minus 4x minus, let's see, 12. Everyone jot down the function first, because I'm going to take this down and I'm going to go look at the homework, and I'm going to tell you what homework I want you to do. Y'all can work together, but I want everyone to do their own work. You're not turning it in, but I'm going to check it off. You can't leave until you have your final picture and it looks beautiful. But I'm going to say after this, you can go as soon as you get it done. I'll sign you out when I see your finished work. Everyone have it? Good. Okay, below the problem is the homework assignment. That goes with this section. I haven't finished it. We still need to do applications. We'll do that next time. But it's on page 3738, problems 1 through 8. They ask you to graph, axis of symmetry, all this stuff.